Imagine a world. If this was a movie trailer, I'd say, in a world where the universe is the two-dimensional surface of a balloon, covered with little dots. Each dot represents a galaxy, star, or planetary body. In this model, the universe is the surface of the balloon, not above it or inside of it. That is empty space. It doesn't exist. Or at least it doesn't exist to us living on the surface of the balloon. Now, as the balloon expands, and before we veer into philosophical discussion about who was blowing up the balloon, let's nip that in the bud. It's an elephant. Hey, it's my visualization, and I don't want to talk about the elephant in the room. As the surface of the balloon expands, as space expands from the Big Bang, all of the objects move away from each other. So what is at the center? Well, from the perspective of every flat Stanley living on one of those dots, they are all at the center because everything is moving away from everything else, from them. Now, let's zoom in on one of those dots, imagining that it is the Earth in its solar system. Imagine that where the Earth sits on the surface of the balloon, it causes a depression on the rubber surface. The rubber surface of the balloon represents the fabric of space and time. The mass of the Earth bends the fabric of space. The larger the mass, the bigger the depression in the fabric of space and time. Now imagine a small comet, the red line on the illustration, is moving through the solar system. As it passes near the Earth, it follows the contour of the bent fabric of space, which changes its trajectory. If far enough away, it would not be affected. If too close, or moving too slowly, the comet would get caught in the gravity well created by the Earth and crash into its surface. This is how gravity works according to Einstein's theory of general relativity. We often think of gravity as the attraction between two objects with mass, and this is how they behave, like two magnets attracted to each other. Bigger objects with more magnetism, and the closer they get, the more they are attracted to each other. But that is a misconception based on our lived experience with objects such as magnets that then provides us with this misconception. The reality, which holds up to math more complex than I can explain, and experimentation that I honestly only truly understand in the abstract, appears to be much more complex, with the curvature of spacetime accounting for the behaviors of objects with mass. But this math and these experimentations continually hold up to scrutiny, and thus allows engineers to build and put into orbit satellites. By knowing their mass exactly, and then putting them outside the drag-averse atmosphere, and then giving them a push at exactly the right speed, they will stay in orbit around the Earth. Too fast and they head off into space, too slow and they burn up in the atmosphere. This also can explain why, counterintuitive as it may be that all objects, negating wind resistance, fall at 32 meters per second towards the Earth. Consider this, all objects on the Earth that we can manipulate to experiment with are but an inconsequential speck in mass as compared to the Earth. So, while a car, a rock, a house have mass, and that mass does cause a curvature in space-time, compared to the Earth's mass, and therefore curvature of space-time caused by the Earth, they are all virtually the same, so they accelerate at the same rate. But don't take just my word for it. Let's look at an actual experiment looking at the effect of gravity on two different sized objects.
A good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that?
How about
Which proves that Mr. Galileo was correct in his findings.
Superb.